Hey folks, today we're going to start off with a application of the stuff we've been doing with functions to sort of the economics of a business. The main, I guess the big variable, the quantity that we'll be looking at most, so we're going to use X for that, is going to be the production level of a company. So this would be how much of your product you make in some time interval. It could be hourly production or by the week or even by the year, maybe longer periods. But you're going to make so many or so much of your product that you're going to sell. Now there's some funny assumptions about production. The first one, which is actually somewhat unreasonable, but it's going to let us make the analysis work, is that we'll sell everything we produce. Now, I guess that's not unreasonable if you think of production as something that you can control, that you can change the production. So you would only make as much as you could sell, right? But the truth of the matter is what a company has control of is the price that they sell their product for. You change the price and that changes the demand. We don't have to talk about economical science very much to get to that point. I think everybody knows that if you make a product more expensive, you're going to sell less of it. If you make it less expensive, you'll sell more. Although there are times when that reverses. There's a famous example of a company that makes fashion accessories, purses or bags for. They were not doing that great, and they raised their prices, and then they did much better. So it was like people bought it because it was more expensive. But usually, more expensive means less of the thing is sold, and vice versa. So ordinarily you think you can control the price, but what we're going to do is a little bit backwards. We're going to set the price based on how much we intend to sell. So P is going to be the price of the things we're producing. And you're going to think about that price as a function of X. In other words, you have P of X. In reality, it's the functional relationship between these is reversed. You control the price. Price is the independent variable, and X, the amount of stuff you'll sell, and hence the amount of stuff you want to produce, is a function of that. So this is slightly backwards. I'm just maybe make a note of that. This is actually backwards. If you think about price and amount sold, they're generally going to have this kind of relationship, right? That is, when the price is low, the amount sold will be high. When the price is high, the amount sold will be low. The thing we're doing here is reversing the roles of these axes. So we're getting a way in which we think the X is the independent variable and the price is determined from that. So it's just imagine taking this image and flipping it around. You'd still have something that looks generally like a downhill thing. If you don't plan to sell many of the product, set the price high. If you want to sell a lot of them, set the price low. So we're using this version, even though this is more closely aligned with reality. It's just because it makes the analysis we're going to do easier. Okay, so that's your basic setup. You've got production, you've got price. There are a couple of functions that you're interested in where they tell you stuff about the amount of money you're going to make, right? So that's actually the goal here, is to maximize the amount of money you're going to make. The first function we're going to talk about is the cost function. And this is the total cost of producing X units. I say units because I'm usually thinking of these as being discrete things. Of course, if your thing you're producing it comes in a mass, you can often still think about that. Like oil productivity, you can produce any amount of oil, but usually you chunk it off into barrels or gallons or something, right? So you can still think of when it's a continuously varying quantity that you're creating. You can still think about breaking it up into units. So we'll call this function C of X for cost. And you can sort of say some things about C of X, crudely, what it looks like. Generally speaking, as X goes higher, it's going to cost more. If you're making, 1,000 cars a week, that's going to cost a certain amount, but if you make 2,000 cars a week, it's going to cost you more. The materials that go into making your product are going to cause the cost to increase. But there's also, it's weird, there's a positive amount that's associated with the y-axis or the c-axis. That is, there's an amount it costs you to produce nothing, which seems weird. It's that these are what are known as fixed costs. They're costs that are there even if you've got the plant shut down and you're not making anything. The cost of paying the employees, the cost of keeping the lights on. The cost of paying the employees may be increased as you produce more and more. You may have to run second shifts and stuff, but there's a core group of people that you can't fire or you're literally just going out of business. So there's that. There's the rent on your property or mortgage payments on it if you own the property. So all these costs that don't change with the amount of production are incorporated into this fixed cost idea. And anyway, from there you expect the cost function to increase. I'll point out though that as you go to higher and higher production levels, the rate at which it increases lessens. That is, it's called economies of scale. When you're buying 100 of some product each week, that's an ingredient into making your stuff, it costs you more than later on when you're buying 200 of it. The people give you a quantity discount. So this cost function does tend to curve over. I don't think it ever curves downward, but maybe in some extreme cases. So yeah, that's the general shape of the curve. Fixed costs followed by some sort of increasing but concave downward graph, C of X. Often we'll ignore the economies of scale stuff and it'll just be a line. So in fact, I'm going to give an example where it's just a line. There's also another function that people are interested in, which is how much money does selling X units of our product bring in? That's called revenue. Well, I should follow the same layout I just did. I want to say the revenue function. That is the total income produced by selling X units. And so that, like I started to write, that's r of x. That is actually pretty easy to compute because remember the two variables I started out with on the previous screen? They were x, the amount we produce and sell, and p, the price that we sell it for. Well, the amount of money that comes in is the price times the how many. This is just x times p. So you can sort of immediately figure out the revenue function. You may need to have p written as it's supposed to be as a function of x, but well, that's not so hard to do either. Okay, and finally, I'm not quite got space for it, but I'll start again at the top. There's the profit function. How much money do we actually generate from our economic activity here of producing X units? And we had C of X and R of X for cost and revenue. The profit function is P of X. Universally, everybody calls profit capital P. Notice the difference between the capital P for profit and the lowercase p for price. But that's the total profit gotten from, oops, bad spacing. And so, actually, that's pretty easy in terms of algebraic manipulation we're going to do with the C of X and the R of X. You have this relationship. Profit, the amount of money you get to stick in your pocket at the end of the day, is how much money did you bring in minus what did it cost you to bring that money in. So revenue minus costs. I think that moment right there is where what the point of including this topic in this section is. It's saying to you that, yeah, here's something that's actually meaningful and people care a lot about. That is an algebraic manipulation that you do with two different functions. So you have a revenue function, you have a cost function, you subtract them, and that'll get you a profit. There actually is one other function that they mention in this section, which is also showing you an algebraic manipulation. This is called the average cost. And you can think of it as a cost per unit. It's how much it costs you to make one of a thing. The problem is that it depends on production level. If I'm making, well, think about, the company Tesla that's been, I don't know, maybe 10 years it's been around. The very first electric car they made probably cost them $20-30 million because of, making tools, hiring people, lots of infrastructure had to be in place before they could make that first car. Now, each car that they make, now that they're selling millions a year, well, maybe not millions, but hundreds of thousands a year, now each car probably costs them, half of what they're selling them for, so 20 grand, something like that. So the cost per vehicle or the cost per unit of your product changes based on how much productivity you're doing. Anyway, its name is C with a bar over it. And you literally say C bar when you see that. It is just take the cost function for making X things and divide it by X. So again, we've got a function that people care about a little bit. How much is, on average, is it costing you to make one of your product? And it's an algebraic manipulation with two functions. The cost function's in the numerator. That seems like, well, it's not a function, but it is. It's just the they call it the identity function, the function that just is the same as the input. So division is used in some cases. So we've got an example for subtraction and an example for division out of this economics example that we're running. I'm getting examples out of an example. Okay. Let me get one more level into this meta of examples. We'll do a physical example of this setup. So the example I want to do is a bicycle shop. It's a small kind of mom and pop operation where you're buying kits. I am not spelling buying right there. B-U-Y. So you buy these kits from China, actually, and the guy I'm thinking of buys kits for this bike's called Giants. And so anyway, you buy the kits, and they're not that expensive. It's about $100 for the kit. The problem is you got to assemble it into a bike and tune it up and get it ready to go. So you buy kits and assemble them, and then you can sell them for a fair bit more than the kit cost. So in this case, just for round numbers, I'm going to say the fixed costs of this business are about $1,000 a week. So that includes, the utility bills, the rent on the facility that they assemble the kits in, paying the workers and stuff. Even if you don't put the workers to work in a particular week, you still got to pay them. It does get, if it gets to the point where you're not going to be doing any production for a month or more at a time, you lay them off and they have to go get unemployment. But let's just assume we're not in dire straits and that they can continue to pay them even if they don't need to be producing much. So that's your fixed cost. The variable cost is the price for the kits, and that is the cost that depends on how many bikes you're assembling. I'm just going to make it nice and easy, so we'll have a round number here. Let's say it's $1 per kit. Sorry, $100 per kit. One would be a little bit cheaper than I could really do. $100 per unit. Okay. So from that information, you can build the cost function. It's going to look like this. C of x is this fixed amount, 1,000, plus for every x, you're going to have $100 of variable costs. The two of those bits together are the total of what it's going to cost you to produce x units. So that's cost. Now, revenue, let's assume, again, just to keep nice round numbers, assume these kits that once they've been assembled into a finished bike, you can sell them for $200. So then your revenue function, R of x, is 200 times your production level. And then that makes your profit revenue minus costs, right? So 200x minus 1,000 plus 100x. All right, so let's see if I can compute here. The like terms are the things involving x. So we have 200 and then 100 being subtracted. So that's 100x minus 1,000. So from that, you can calculate something that's kind of nice to know. It's called the break-even point. How much productivity do you have to stop losing money? For instance, is it very clear that if x was 0, you're losing $1,000 a week? That's not good. Where does X need to be for you to break even, to not be losing money? And because I kept nice round numbers, that's easy too, isn't it? 10? If X was 10, we'd have 1,000 minus 1,000, 0. So no profit, but at least we're not losing money. What we really often like to do is figure out what's the production level that would get us the most money. And in this case, that doesn't have a good answer. Think of what the graph of this profit function would be. It's a straight line. It has a y-intercept at minus 1,000. Has a x-intercept, that's the value we just computed, the break-even point at 10. So I'm going to put that there. The scales on these things are very different. Where thousands of dollars is about 2 inches vertically, but thousands of bikes would be way, way out there. So this is just 10 bikes. So I've made 10 and 1,000 have about the same size on the scales of these axes. Still, this is the equation of a line, isn't it? It's got a m, 100 times x, and a b, negative 1,000. So it's a straight line, and I've already got 2 points on the line, so I can tell you what the graph looks like. I went and started making it look like it curves. It doesn't. It's a straight line. Goes that way. The domain of really of all of these functions is, well, it's constrained a little bit by reality. You can't have negative production levels, can you? Can you make -3 bicycles? I guess you could have people return the bikes and you disassemble them and put them back into the kits. No, that probably doesn't make sense. So the domain of all of these things is from 0 upward. So this piece of the graph that I drew shouldn't be there. The function is defined from 0 into positive values. And if we want to make more money, we just keep making more bikes. Right? So this is just consistently going higher and higher and higher. If we get to 20 bikes per week, we're going to be making $1,000 per week. If we make it to 30, it'll be 2,000, and so on. So according to what I've done thus far, we should just try to produce production until we're making millions of bikes. Well, what happens if you do that? We'll see that our revenue function is actually unrealistic in that case. Because if you want to sell millions of something, you've got to sell them at a cheaper price than if you want to sell hundreds of something. So this revenue function is actually somewhat unrealistic. We'll come back to it. We'll get a more realistic revenue function, and you'll see the typical shape for a profit curve is more like this kind of thing. You start low, you start down below, you have your break-even point. You reach some point where you're making the most money possible, and then if you try to go beyond that, you actually fall off. So there's a max. There's a maximum value you'll get at. The problem is that in order to get your production even higher, you have to drop your prices, and your costs may not drop as quickly as your prices would need to. So you get to this point where it's actually not worth it to try to increase productivity anymore. It's better to get yourself at that max and kind of hang here there. So I'm going to change that example to give us something that's a little bit more realistic. The problem with what I just did was I had the price to production level the relationship between price and the amount we'd sell, which is the same as production level, as just a fixed number. And that's not realistic. So suppose we had 2 data points at a price of $300 per bike. We don't sell any. Because, maybe there's a competitor that has prices that are better than that, or people just go, well, it's too expensive, they're not going to do it. And at $200 per bike, we're selling 20. So given those two data points, pretty much the only rational connection you can make between them is to draw a straight line. Now, a straight line between those points probably isn't, the best way you could model this, but it's something. So let's see what that line would look like. Got to remember that we've got x on the horizontal axis and price on the vertical axis. And so when we said $300 per bike, we sell 0. 0 is the amount of production, or the amount we sell. That's here on the x-axis, and $300 is up here. So that's a point right there whose coordinates are 0, 300. This other data point we have, $200 per bike, we're going to be selling 20. Well, 20 is right there on the x-axis, and $200 per bike would be about there, so something like that. And so we'll get the straight line in between those things, those 2 points. Again, the domain of the function is such that we really wouldn't have any graph out there in the negative x territory. But, as a line, it does continue in both directions. What would the equation of that line be? Well, we've got a y-intercept of 300 here, but what is the slope of it? Do you see that, I didn't say what this point was, 20, 200. You see that we're moving sideways 20 units, and we are dropping vertically 100 units. We're going from 300 down to 200. So the slope on that guy is minus 100 divided by 20, which is negative 5. So that means we can write the p as a function of x using the mx plus b form for a line. So p is 300 minus 5x. I guess that's the b plus mx form. I wrote it backwards. When I've got a negative slope, I tend to do that and write the slope on the back side. Same thing as saying minus 5x plus 300, isn't it? So if that's our relationship between price and amount sold or produced, we get a much more realistic example here. That doesn't affect our cost function. So c of x is going to remain 1,000 plus 100x. It affects our revenue function, however. R of x is now x times price, but that's going to be x times 300 minus 5x. And so our profit function, p of x, is revenue minus cost. I'm going to go ahead and distribute the x into this guy first. So that'll be our revenue function, 300x minus 5x squared. And then we will then subtract the cost function, which is 1,000 plus 100x. And then let's work on that to try to simplify it. That is a polynomial expression with terms that have degree 2, 1, and 0. So we just want to combine all the like terms. The only one that's quadratic, that has x to the second power, is up front. Is that one right there, minus 5x squared. And then we have two of them that have just an x in them, 300x here, and then we're subtracting 100x, so 200x, positive 200x, yeah. And then the only one that's a constant is this 1,000 here, which is being subtracted, so minus 1,000. I'd like to graph that for you. There's a couple of ways you can do it by hand, but I don't want to get into by hand graphing at this point. So it would be probably best to use a calculator or Desmos. All right, so I've gone ahead and entered the thing into Desmos there, and I think that should be a good view of it for you. Minus 5x squared plus 200x minus 1,000. The problem we're seeing is that what you get is this vertical red line in it. Let me turn it into projector mode so that shows up a little better, right? And that looks pretty weird, like maybe we're not seeing all of the graph. And that's the problem with it. We're not seeing very much of the graph. So let me pinch to zoom. Oh, there's another piece of the graph over here. So at this scale, it looks like the graph is two vertical lines. And it's not. It's actually doing what I said before. It's starting out in negative territory. In other words, we're making a loss. And then it's ascending up to a maximum. And then it's coming back down. But the maximum is way off our screen. It's way up here. So we need to scale things so that the x and the y-axis are different. Oops. Well, let's do it through the setup here. You can change the numbers on the axes independently of one another if you go into the setup there. So we want the y-axis to go from minus 1,000. Wasn't it $1,000 that we're losing if we... Okay. And apparently taller than it is here. So that minus 1,000 caught our maximum loss at a production of 0. We're losing $1,000 a week. Well, now you can sort of see what's the graph looking like. It turns out somewhere right around that, I can't tell what that production level is. Is it 20? Yeah, at 20 bikes per week, we're making $1,000 per week. That's actually, probably not worth your while to run a business that only nets you $1,000 a week. So, but remember I chose like nice round numbers for us in this example. So, yeah. I imagine the actual owner of a bike shop takes home more than $1,000, or maybe he's got multiple bike shops and they get, yeah, okay.